This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is parallel DC circuit properties. Our objective is to examine the fundamental properties of parallel DC circuits, including Kirchhoff's current law. This lecture operates under the presumption the viewer has more than a nodding acquaintance with DC Ohm's law, power, and parallel resistance calculations. If at any time you feel you're over your head, please take the time to click on the provided links to bring yourself up to speed. A circuit is a complete path or a closed loop. The closed loop could be a single circular, rectangular, triangular, or any other shape forming a complete loop or composed of many different pathways that at least one of which connects one terminal of a voltage source to the other. Without at least a single closed loop, there is no circuit, and there is no way conventional current can flow from the positive terminal of a source to the negative terminal. A closed circuit requires a closed path for current to flow. Circuits consisting of multiple resistors can assume numerous different configurations, one being known as a parallel or side-by-side configuration. A parallel arrangement means there is more than one path for current. Here's an example of a simple parallel circuit consisting of a 12-volt source between node A and B, R1 having a value of 330 ohms, also between node A and B, and R2 having a value of 560 ohms, also between node A and B. If we were to visualize conventional current flowing through the system, you'll note source current would leave the positive terminal of the source and enter node A, where it divides between two paths, one afforded through R1, the other through R2. At node B, the current through R1 and R2 recombine to return to the negative terminal of the source. More than one path for current exists in parallel circuits, in this case, two. An important observation can be made regarding voltage in simple parallel circuits. Voltage across elements in parallel is the same. This is perhaps the most fundamental of parallel circuit properties, and we'll have ample time and occasion to visit this property on a regular basis to simplify the analysis procedure. You'll note node A is the pooled connection at the top of the circuit, and node B is the pooled connection at the bottom of the circuit. Anything between node A and B will experience a 12-volt differential. I say again, voltage across elements in parallel is the same. The voltage source E establishes a 12-volt differential between nodes A and B. Given both R1 and R2 are between node A and B, we can say both R1 and R2 experience a 12-volt differential. V1 equals 12 volts, as does V2. Any voltmeter measuring the rise established by the source or the drop across either resistor would measure 12 volts. Let's now examine current through individual branches inside this parallel circuit. Given we know voltage across each element to be 12 volts, and we know the resistance of both elements, it's a simple matter of applying Ohm's law to each individual resistor. The current through R1 will be equal to the voltage across it divided by resistance. I1 equals V1 divided by R1. Similarly, current through R2 will be equal to the voltage across it divided by resistance. I2 equals V2 over R2. Before we substitute in our given values, let's make a prediction. Given voltage across each resistor is the same, and current is equal to voltage over resistance, it stands to conjecture that a smaller resistor will draw more current, and a larger resistor will draw less current. I'm willing to wager R1 at 330 ohms will draw more current than R2 at 560 ohms. Let's see if this is the case. Substituting in our given values for R1 demonstrates I1 will be roughly 36.4 milliamperes. Similarly, substituting in our given values for R2 demonstrates I2 to be roughly 21.4 milliamperes. As predicted, the smallest resistor in this parallel circuit draws more current and the larger resistor less. Let's add these observations to our list of parallel DC circuit properties. So far, we've observed the following to be true. 1. Voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. 2. The smallest resistor in a parallel circuit draws the largest amount of current, and the largest resistor in a parallel circuit draws the smallest amount of current. Yet another fundamental parallel circuit property lies easily within our grasp. Given R1 draws 36.4 milliamperes from the source, and R2 draws 21.4 milliamperes from the same source, how much current does the source provide to the complete circuit? Obviously, the source must provide 36.4 plus 21.4 for a total of roughly 57.8 milliamperes. This is Kirchhoff's current law, which states for any given node, the sum of currents entering the node must equal the sum of currents leaving the node. Stated in a different fashion, what goes in must come out. You will note that at node A, 57.8 milliamperes of current enters and then splits into two unequal paths of 36.4 milliamperes and 21.4 milliamperes, where the proportion of current entering a particular branch is reflective of the resistance of that particular branch. At node A, we can say I source equals I1 plus I2. 57.8 does indeed equal 36.4 plus 21.4. Similarly, at node B, 36.4 milliamperes and 21.4 milliamperes enter node B, and 57.8 milliamperes leaves. At node B, we can say I1 plus I2 equals I source. 36.4 plus 21.4 does indeed equal 57.8. If this seems too easy to you, we can verify source current using Ohm's law. As you are no doubt aware, one can simplify parallel circuits into a total resistance seen by the source using one of two formulas, one being a special purpose shortcut formula for two resistors in parallel, and another being a more cumbersome formula for any number of resistors in parallel. Substituting our given values into either formula would result in a total resistance of roughly 207.6 ohms. This implies that the source would be none the wiser if the parallel combination of two resistors was swapped out and a single 207.6 ohm resistor took their place. This easier visualization could be used to verify our earlier calculations. Making use of this simplification, an application of Ohm's law confirms that the 12-volt source would indeed push roughly 57.8 milliamperes of current through this system. While one can perform this simplification and subsequent Ohm's law calculation, it's often far easier to summate individual branch currents to determine source current using Kirchhoff's current law, since it uses simple addition and subtraction. Let's review the fundamental parallel circuit properties we've discussed thus far. 1. Voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. 2. The smallest resistor in a parallel circuit draws the largest amount of current, and the largest resistor in a parallel circuit draws the smallest amount of current. 3. Kirchhoff's current law, which states for any node, the sum of currents entering the node must equal the sum of currents leaving the node. In summary, what comes in must come out. Let's now examine power distribution in parallel circuits. Let's look at the individual elements first. As you are no doubt aware, power is equal to voltage times current. Given voltage across elements in parallel is the same, most likely the branch that draws the most amount of current will consume the most power. Conversely, the branch that draws the least amount of current will consume the least amount of power. Let's see if this is the case. The power dissipated by R1 is equal to the voltage across it times the current through it. P1 equals V1 times I1. Substituting our given values demonstrates R1 dissipates roughly 436.4 milliwatts of power. Similarly, the power dissipated by R2 is equal to the voltage across it times the current through it. P2 equals V2 times I2. Substituting our given values demonstrates R2 dissipates roughly 257.1 milliwatts of power. As we predicted, not only does the smallest resistor in a parallel circuit draw the largest amount of current, it also dissipates the largest amount of power. Conversely, not only does the largest resistor in a parallel circuit draw the smallest amount of current, it also dissipates the smallest amount of power. Let's now consider power dissipated by the complete system. As you are no doubt aware, power input to a system always equals power output. For this system, power total equals P1 plus P2. Substituting our calculated values for P1 and P2 demonstrates that the source must provide roughly 693.5 milliwatts to this system. There exist ample opportunities for us to check our work. Consider this simplified circuit consisting of a 12-volt source and a 207.6 ohm total resistance. An application of any and all the permutations of power equations similarly demonstrate that the source provides roughly 693.5 milliwatts of total power to this system. Let's add these power observations to our growing list of parallel circuit properties. 1. Voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. For this circuit, E equals V1, which equals V2, and they all equal 12 volts. 2. The smallest resistor in a parallel circuit draws the largest amount of current, and the largest resistor in a parallel circuit draws the smallest amount of current. 3. Kirchhoff's current law, which states for any node, the sum of currents entering the node must equal the sum of currents leaving the node. For this circuit, I source equals I1 plus I2. In summary, what comes in must come out. 4. power in equals power out. For this circuit, power total equals P1 plus P2. And finally 5, the smallest resistor in a parallel circuit dissipates the largest amount of power, and the largest resistor in a parallel circuit dissipates the least amount of power. These observations constitute fundamental properties for all parallel circuits and serve as both a great way of simplifying the analysis procedure and an excellent means of checking your work. If your calculations suggest conclusions not in agreement with these properties, you are doing it wrong, and you need to perform a tactical retreat or reassess your data. Let's modify our existing circuit ever so slightly by adding an additional path in parallel in the form of R3, a 470 ohm resistor. My question to you is this: how does the addition of this third path affect electrical properties in the original two paths? i.e., does the presence or absence of R3 in any way, shape, or form affect the voltage across, the current through, and the power dissipated by R1 and R2? If you're tracking, you should realize R1 and R2 don't give a damn about the new neighbor, and will continue to respectively chug 36.4 milliamperes and 21.4 milliamperes from the source, whether R3 is there or not, because voltage across elements in parallel is the same. Given R3 is also positioned between nodes A and B, we can say V3 also equals 12 volts because voltage across elements in parallel is the same. This again is the most fundamental parallel circuit property. For this circuit, E equals V1, which equals V2, which equals V3, and they all equal 12 volts. As an exercise to the viewer, I invite you to solve for the current drawn by and the power dissipated by R3 in this present configuration. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following data. The current through R3 will be equal to the voltage across it divided by its resistance. I3 equals V3 over I3. Substituting our given values demonstrates I3 will be roughly 25.5 milliamperes. Power dissipated by R3 will be equal to the voltage across it times the current through it. P3 equals V3 times I3. Substituting our given values demonstrates P3 will be roughly 306.4 milliwatts of power. Now that we've got these figures for all three elements, let's determine source current and total power for the complete circuit. You note that while the addition of R3 in parallel does not affect the electrical properties of R1 and R2, it does affect the source because yet another path for current exists, and as such, the source must provide more current and more power. If you want to think of it this way, the source has another hungry mouth to feed. An application of Kirchhoff's current law demonstrates that I source equals I1 plus I2 plus I3. Given power in always equals power out, P total should equal P1 plus P2 plus P3. As an exercise to the viewer, I invite you to use Kirchhoff's current law and power properties to determine source current and total power. Additionally, see if you can simplify this parallel circuit consisting of three elements into a single total resistance, and then use Ohm's law and the power equations to check your work. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Substituting our calculated values for I1, I2, and I3 into the Kirchhoff's current law equation for this circuit demonstrates source current has risen to 83.3 milliamperes. Similarly, substituting in our calculated values for P1, P2, and P3 into the power distribution equation demonstrates total power has risen to roughly 999.9 milliwatts, just 0.1 milliwatts shy of a full watt. Let's use Ohm's law and the power equations to check our work. The total resistance seen by the source is roughly 144 ohms. This implies the source would be none the wiser if the parallel combination of three resistors was swapped out and a single 144 ohm resistor took their place. This easier visualization can be used to verify our earlier calculations. Making use of this simplification, an application of Ohm's law confirms that the 12-volt source would indeed push roughly 83.3 milliamperes of current through this system. An application of any and all the permutations of the power equations to the simplified circuit confirms the source provides roughly 999.9 milliwatts of total power to this system. Is it just me, or does parallel circuit analysis seem easy? Yes, it is, and it should be. Voltage across elements in parallel is the same, and properties like Kirchhoff's current law make parallel circuit analysis astoundingly easy. You'll additionally note rearrangement of the resistors constituting the parallel relationship does not in any way, shape, or form affect current drawn or power dissipated by individual elements, nor does it affect source current or total power. Consider R3, R1, R2 in a parallel configuration with a 12-volt source. Given voltage across elements in parallel is the same, V3, V1, and V2 remain 12 volts, and R3 continues to draw 25.5 milliamperes of current, R1 continues to draw 36.4 milliamperes of current, R2 continues to draw 21.4 milliamperes of current, and the source continues to supply 25.5 plus 36.4 plus 21.4 or 83.3 milliamperes of current as previously. Absolutely nothing experienced by the individual elements deviates in the slightest manner. Perhaps the most difficult aspect of parallel circuits for first-timers is incorporating ammeters into real-world parallel circuits to measure specific branch currents and source current. You'll no doubt recall that an ammeter must be placed in series or in line with the element under inspection. Ammeters necessitate the modification of the original circuit to do so. Consider an ammeter inserted in this system intended to measure source current. Source current leaves the positive terminal of the power supply and enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, and then enters node A, where it splits into three distinct paths, one through R1, another through R2, and a third through R3. Source current recombines at node B and returns to the negative terminal of the source. The ammeter captures outbound current for all three paths in this parallel system. An ammeter configured in this fashion would read roughly 83.3 milliamperes of current. Here's another way of inserting an ammeter into the system to measure source current. Source current leaves the positive terminal of the power supply and immediately enters node A, where it splits into three distinct paths, one through R1, another through R2, and a third through R3. Three branches of current recombine at node B, enter the ammeter indoor, travel through the ammeter, leave the ammeter outdoor, then return to the negative terminal of the source. An ammeter configured in this fashion would read roughly 83.3 milliamperes of current. If, however, we wish to measure current through individual parallel branches, we need to insert the ammeter inside each branch of interest, such that it measures current in the branch of interest and the current in the branch of interest alone. Consider an ammeter inserted in the system intended to measure I1. Source current leaves the positive terminal of the power supply, enters node A, and immediately splits into three distinct paths. One bound for R2, another bound for R3, another bound for R1. Current inside the R1 branch enters the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, into R1, through R1, out of R1, and then joins up with I2 and I3 at node B and returns to the negative terminal of the source. The ammeter captures current through R1 and current through R1 only. An ammeter configured in this fashion would read roughly 36.4 milliamperes of current. Here's another way of inserting an ammeter into the system to measure I1. Source current leaves the positive terminal of the power supply, enters node A, and immediately splits into three distinct paths, one through R2, another through R3, and another through R1. Current inside the R1 branch travels into R1, through R1, out of R1, into the ammeter indoor, travels through the ammeter, leaves the ammeter outdoor, and then joins up with I2 and I3 at node B and returns to the negative terminal of the source. Again, the ammeter captures current through R1 and current through R1 only. An ammeter configured in this fashion would read roughly 36.4 milliamperes of current. Again, in each scenario, you will note the ammeter is arranged such that it is in series or in line with the element of interest, in this case, R1. Let's see if you've got a solid understanding of this concept. As an exercise to the viewer, I invite you to illustrate how to incorporate an ammeter to measure I2 and I2 only. Similarly, I invite you to illustrate how to incorporate an ammeter in this system to measure I3 and I3 only. By all means, pause the lecture and try this on your own. If you're tracking, your circuits should look something like this. You'll note in each scenario, the ammeter is configured such that it is in series or in line with the element under inspection only. An ammeter configured in the top fashion would read I2 and I2 only and should measure 21.4 milliamperes. Similarly, an ammeter configured in the bottom fashion would read I3 and I3 only and should measure 25.5 milliamperes. As an additional challenge exercise to the viewer, I invite you to predict the amount of current measured by ammeters configured in the following two fashions. If you're struggling, here's a hint. Use Kirchhoff's current law and visualize how current flows through this system. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The top diagram shows an ammeter measuring current bound for both R1 and R2. This ammeter would read 36.4 plus 21.4 or 57.8 milliamperes. The remaining 25.5 milliamperes of current bound for R3 would be unmeasured. The bottom diagram, in contrast, shows an ammeter measuring current bound for both R2 and R3. This ammeter would read 21.4 plus 25.5, or 46.9 milliamperes. The remaining 36.4 milliamperes of current bound for R1 would be unmeasured. Alright, let's now discuss the influence of shorts and opens in parallel circuits before we bring this lecture to a close. As a preparatory exercise to the viewer, I invite you to solve for the voltage across each element, the current through each element, the power dissipated by each element, source current, and total power for the complete circuit. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Now, before you start punching numbers into your calculator, first begin with an inventory of things we know about parallel circuits. Voltage across elements in parallel is the same. E equals V1, which equals V2, which equals V3, and they all equal 16 volts. Kirchhoff's current law, which states the sum of currents entering a node will be equal to the sum of currents leaving a node. In summary, what goes in must come out. For this circuit, I source equals I1 plus I2 plus I3. Given R1 is the smallest resistor, it will most likely draw the largest amount of current and dissipate the most amount of power. Conversely, R3 is the largest resistor and it will most likely draw the smallest amount of current and dissipate the least amount of power. Given the relationship of R1 and R3, one might expect I1 to be twice as much as I3. Finally, power in equals power out. For this circuit, total power equals P1 plus P2 plus P3. Given these predictions, we've got a well-defined landing zone inside which we anticipate our results to drop. If any results fall outside this zone, they're wrong, and we need to revisit our calculations. Current is equal to voltage times resistance. I1 equals V1 over R1. Substituting our given values demonstrates I1 equals roughly 66.7 milliamperes. Power equals voltage times current. P1 equals V1 times I1. Substituting our given values demonstrates R1 dissipates roughly 1.1 watts of power. Let's solve for these same properties for R2. I2 equals V2 over R2. Substituting in our given values demonstrates I2 equals roughly 41 milliamperes. P2 equals V2 times I2. Substituting our given values demonstrates R2 dissipates roughly 656.4 milliwatts of power. Let's solve for these same properties for R3. I3 equals V3 over R3. Substituting our given values demonstrates I3 equals roughly 33.3 milliamperes. P3 equals V3 times I3. Substituting our given values demonstrates R3 dissipates roughly 533.3 milliwatts of power. You note the smallest resistor, R1, appears to be drawing twice as much current and dissipating twice as much power as the largest resistor, R3. It makes sense. R1 has half the resistance as R3, and these properties are evidence of this fact. Let's now examine source current and total power. Source current equals I1 plus I2 plus I3. Substituting in our calculated values demonstrates source current equals roughly 141 milliamperes. Power in equals power out. For this circuit, total power equals P1 plus P2 plus P3. Substituting in our calculated values for P1, P2, and P3 demonstrates that P total equals roughly 2.3 watts. Let's check our work. The total resistance of these three parallel resistors equals roughly 113.5 ohms. Using this simplification, an application of Ohm's law confirms source current to be roughly 141 milliamperes. Total power equals supply voltage times source current. Substituting in our given values demonstrates that total power does indeed equal roughly 2.3 watts. I've got a reasonable degree of confidence our answers are correct. Before we move on to discuss opens and shorts inside parallel circuits, take a moment to reflect not upon the minute details of calculation, but rather the larger procedure we use to solve for the desired properties of this system. At no point did we wander off the path and start blindly thrashing about, uncertain of our destination. At all times, we were aware and informed of our goals and those pieces of knowledge leading to those goals. We took an inventory of what we did know and used items in this inventory to quickly arrive and confirm our results. As a result, we got the correct results the first time in the quickest manner possible. This is the standard of success. Circuit analysis, at its core, is an understanding of the fundamental properties of those circuits under inspection and then putting them to use in an organized fashion. For parallel circuits, these properties are as follows. 1. Voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. 2. The smallest resistor in a parallel circuit draws the largest amount of current, and the largest resistor in a parallel circuit draws the smallest amount of current. 3. Kirchhoff's current law, which states for any node, the sum of currents entering the node must equal the sum of currents leaving the node. In summary, what goes in must come out. 4. Power in always equals power out. And finally, 5. The smallest resistor in a parallel circuit dissipates the largest amount of power, and the largest resistor in a parallel circuit dissipates the least amount of power. Finally, Ohm's law and the power equations work all the time. They work for individual elements and simplifications of larger circuits. You can use Ohm's law at night, all day long, right side up, upside down, underwater, or out in space. You simply cannot exist, let alone function, without Ohm's law. Get good at Ohm's law and use it often. Beyond the knowledge of these fundamental properties and an aptitude for calculation, one must be systematic and organized. I'm sorry, but I cannot teach you to be organized. That was your mama's job. My advice is to write intermediate simplifications and results down. That way you can always return to these values at later points to check your work. Use the history in your calculator. Only round the final answer. Always use unrounded numbers for all calculation purposes. Keep track of where you are, and at the very least, know where you're supposed to be going. Moving on. Now that we've got a complete understanding of the base state of this system, let's examine the influence of opens and shorts in parallel circuits. Let's look at opens first. Consider an open between node A and the top of R1. R1 is effectively removed from the circuit, and no voltage appears across, nor will any current flow through it. R2 and R3, those resistors still in the circuit, however, continue merrily chugging away as if nothing has happened. In this case, the source only needs to provide 41 plus 33.3, or roughly 74.3 milliamperes. In summary, opened elements in parallel circuits remove only the opened element from consideration. This is perhaps one of the best features about parallel circuits. By selectively opening and closing the path to one element, that element and that element alone is selectively energized and de-energized, and in no way, shape, or form affects the operation of other elements in this system. If R1, R2, and R3 represented electrical loads in 3 separate rooms, one could turn on or off loads in specific rooms by placing a switch inside each branch circuit. With all switches open, no loads draw current. When switch 1 closes, only the electrical loads in room 1 are energized. When switch 3 closes, the electrical loads in room 3 are additionally energized. When switch 1 opens, the electrical loads in room 1 are de-energized. You get the picture. Opens can occur in other places in parallel circuits. Consider an open between the positive terminal of the source and node A, effectively severing the entire parallel circuit from the source. No voltage appears across, nor will any current flow through any element. The entire system is depowered. You might functionally see a master switch or master circuit breaker configured in this fashion to enable or disable the complete system. With the master switch open, no electrical load can be energized regardless of the status of individual branch circuit switches. Conversely, with the master switch closed, the status of an individual branch circuit switch can now control the electrical load under its direction. Let's now examine the influence of short circuits inside parallel circuits. As you are no doubt aware, a 0 ohm short directly across the terminals of a voltage source is a bad idea under full sail. A short presents no opposition to current flow, and theoretically infinite current can flow. Theoretically. This isn't really true. We live in the real world, and real-world devices can't produce infinite current. In the real world, you're going to run into one of two scenarios, either a current-limited source or an overcurrent protected source. Allow me to demonstrate. Consider our original parallel circuit consisting of a 16-volt source and 3 resistors in parallel. Let's say this is a variable voltage source that is current limited to a maximum of 1 amp. Any current draw in excess of 1 amp and the source will actively drop voltage such that a maximum of 1 amp flows through the system. You recall, we examine the current limitation feature in the DC power supplies lecture, available at the Big Bad Tech channel. In the unmodified state, 141 milliamperes of source current is well below the upper limit of 1 amp, and everything functions as you'd expect. If, however, low resistance short, on the order of, let's say, 100 milliohms, is placed from terminal A to B, another path with extremely low opposition to current exists, and substantial current through the short will flow. The parallel combination of R1, R2, R3, and the 100 milliohm short presents a resistance of only roughly 99.9 milliohms. An application of Ohm's law demonstrates that the current limited voltage source needs to provide only roughly 99.9 millivolts, such that 1 amp flows through this system. A majority, 99.1 milliamperes, travels through the short, 416.3 microamps travels through R1, 256.2 microamps travels through R2, and the remaining 208.1 microamps travels through R3. In summary, a short circuit inside a parallel circuit wrecks the whole circuit. In this application, a current-limited voltage source actively reduces output voltage such that the current stays below the permitted maximum, in this case 1 amp. Alternatively, the other type of response to short circuits and parallel circuits involve fixed voltage sources with overcurrent protection in series. For example, consider a 1 amp circuit breaker in between the 16-volt source and the original parallel combination of 3 resistors. In this sense, the 1 amp circuit breaker acts like a master switch for the complete circuit. If source current ever exceeds 1 amp, the circuit breaker opens and disconnects the entire circuit. In the unmodified state, the source provides 141 milliamperes, well below the upper limit of 1 amp, and everything functions as you'd expect. If, however, low resistance short, on the order of, let's say, 100 milliohms, is placed from terminal A to B, another path with extremely low opposition to current exists, and substantial current will flow. In this scenario, the fixed voltage source is not current limited and could theoretically provide an infinite amount of current. An application of Ohm's law demonstrates that the short draws 160 amps, and a subsequent application of Kirchhoff's current law demonstrates source current immediately spikes to 160.1 amps. The 1 amp circuit breaker detects current well in excess of its upper permitted maximum and immediately opens to prevent damage to the system. In this application, overcurrent protected sources disconnect the circuit to prevent current from exceeding the permitted maximum. In summary, short circuits inside parallel circuits wreck the whole circuit and are generally to be avoided at all costs. Current limited sources and sources with overcurrent protection are 2 different means of preventing a short from ruining everything. Alright, that's about it for today. We'll examine other topics related to parallel circuits like current sources and the DC current divider rule in later lectures. Until then, that's all I've got for you today regarding parallel DC circuit properties. In conclusion, this lecture took a close look at parallel DC circuit properties. We learned voltage across elements in parallel is the same, and the summation of currents entering a node equals the summation of currents leaving a node. In summary, what goes in must come out. Additionally, we learned the smallest resistor in a parallel circuit draws the largest amount of current and dissipates the most amount of power. Conversely, the largest resistor in a parallel circuit draws the smallest amount of current and dissipates the least amount of power. Finally, we learned that power in always equals power out, and use this and other parallel properties and Ohm's law to check our work. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. I'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.